Okay, so this is take 2 of this, and the first one you don't even want to know what that looked like. Something terrible. 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 Alright, so in the absence of compressed liquid tables, how is the specific volume of a compressed liquid at a given P and T determined? The main issue where you're going to have this is where your P is just going to be tiny. I mean, look at the values on here. Wrong one. Look at the values on here. We got like the smallest possible value for pressure is right here. 5 megapascals. Yeah, I was just everything we've worked with so far has really been, honestly, kilopascals. I mean, look at the saturated tables. They're just like, sorry, that's not saturated, that's superheated. Saturated water. We got a pressure table. That's on the realm of kilopascals for the most part. It does actually get up into 20 megapascals, but usually that's not what we're working in. Usually they're asking like, let's say we got 550 pascals or kilopascals. Yeah, 5 megapascals is not going to make a good estimate, even if you could get the right temperature. Let's see. Yeah, because, well, I guess the temperature is a good range. Anyways. Alright, so there are 2 ways we can consider this. Is that we have the right pressure, excuse me. When we're looking at a PV or a TV diagram, let's go ahead and do a PV diagram. If we're doing a PV or a TV diagram, we have a steam dome. And the walls of the steam dome are pretty steep. There's not much change along there. Now in pressure, we're going from high pressure, like liquids. Liquids are high pressure. To low pressure and vapor. That was a particular problem in my group. Alright, you've got a linear slope here, which is pretty, the flat, let's put it this way. These are pretty much vertical. They're very straight. There's relatively little change, whereas these, there's just huge, really fast change. So if you use the wrong pressure, you know, if your pressure is too high, it's going to give you a specific volume that's just like tiny. Teeny tiny. Not really useful. Alright, now let's say that we have a given pressure. We'll call this P1. This is our given P. And this particular line represents our T1, our given T. Alright, let's also go ahead and set up a volume diagram because, volume. Temperature. TV diagram. Because presumably we're going to have to pretend that we're going to have to focus on either the temperature or the pressure. We can't use both of them the way they are right now. Okay? This is our P1. We're in a compressed liquid area, so this is our T1. Alright. So this is the specific volume that we actually want. This is our V1. This is what we want. Now let's consider the different ways we could do this. We've only got the compressed liquid table, and the superheated vapor tables. Well, we've already determined the compressed liquid table is not going to do us any good. Superheated vapor is going to be even worse. It's not even on the right side of the steam dome. So the only thing we're left with is the saturated water tables. Okay, let's just look at the saturation stuff. Alright, so we have two, basically, that is going to give us okay, so when we do look at the saturated water tables, we are given a via fusion, which is when it turns from gas, liquid mixture into actually being liquid. Okay, so but these tables also have an already a predetermined temperature and pressure matching. See, you've got a given pressure, you've got a given temperature, which means you have to pick: are you going to look at the temperature or are you going to look at the pressure? Alright, so let's go back. So if I choose to keep the same pressure but choose a different temperature, then that is going to give me this value. Let's call this V2. Okay? In this demonstration, it would be the same pressure but a different temperature. So this would be T2. Okay. So this is again V2. That's one option. Or we could choose to keep the temperature constant and change the pressure. In that case, that would find us, let's see, we would have a P2 right here because it's coinciding with the T1. Let's just call this P3 just to keep things from getting confused. Alright, so this is going to be our V3. Well, look at that, it's a lot closer to our V1 than our V2. Well, maybe that's just the way that this PV diagram looks. Let's check it on the T diagram. Alright, so let's say we're keeping the same temperature, but we're choosing the pressure that fits with the temperature. So that means it's going to have this solid line with because this is the saturation temperature. If we're looking at this graph, it's going to be at this table, it's going to be the saturation temperature, which gives us a new P3. Sorry, I'm listening to music in Spanish and I'm starting to try and speak it all of a sudden. Alright, and that again produces a V3, which is right in between V1 and V2. So, if we have no compressed liquid table, and so the closest we can find is a V fusion on a saturated liquid table, saturated vapor table, then of course all we're going to be able to do is choose to have the same temperature, not the same pressure. If we choose the same pressure, then we will wind up with a value that's much larger, presumably, than what we're looking for. Whereas the choosing the same temperature and a different pressure, well, that seems to be a bit closer anyways. Alright, let me go ahead and put T2 on here because I forgot to. Yeah, that's where T2 would produce. Alright, so I hope that made some sort of convoluted sense. Thanks. Bye. Why did I just say bye? I am only finishing this problem.